The F-22 and F-35 defined air superiority for decades, but a new era is dawning.
Every generation brings a leap. 4th gen brought agility, 5th gen brought stealth. 6th generation brings something.
The 6th generation is not just a plane, it is a system of systems. The fighter jet is merely the central.
This generation focuses on information dominance. The jet processes terabytes of data instantly. Visually, the most distinct feature is the tailless design. Removing vertical stabilizers eliminates a major radar reflector, pushing stealth to near invisibility.
5th gen stealth works well against high-frequency radar. 6th gen aims for broadband stealth, remaining invisible even to low-frequency search radars.
The heart of the 6th generation is artificial intelligence. AI is not just an assistant.
This allows for optional manning. The jet can fly autonomously, or the AI can handle the flying while the human focuses on mission strategy.
This leads to the loyal wingman concept. One manned fighter controls a swarm of drones.
These drones act as scouts, weapons carriers, or decoys, extending the pilot's reach and keeping the expensive manned jet out of immediate danger.
In a worst-case scenario, the loyal wingman is expendable. It can intercept incoming fire, sacrificing itself to ensure the human pilot returns home. Powering these beasts is the adaptive cycle engine. This breakthrough allows the engine to switch modes mid-flight for optimal performance.
In combat, the engine configures for maximum thrust and speed, similar to a turbojet, allowing for supersonic dashes and dogfighting.
For long-range cruising, it switches to a high bypass mode like a commercial airliner, significantly extending range and loiter time. These engines also generate massive amounts of electricity and provide better thermal management, cooling the exhaust to hide from heat-seeking missiles.
The massive power generation is required for directed energy weapons. 6th gen fighters are expected to carry operational laser systems.
Lasers provide a near-infinite magazine for defense, capable of shooting down incoming missiles at the speed of light.
Offensively, they will deploy hypersonic missiles. These weapons travel faster than Mach 5, giving enemies seconds to react. The airframe itself is a sensor. Smart Skin technology embeds antennas and radar receivers directly into the fuselage material.
This provides 360-degree situational awareness without the need for external pods or bulky radar domes that compromise stealth.
The United States is leading with the NGAD program Controls, a highly classified project to replace the F-22 Raptor.
The U.S. Navy has its own version, the FAXX, designed for carrier operations with longer range to keep ships safe from anti-access weapons.
Across the Atlantic and Pacific, the UK, Italy, and Japan have joined forces for the Global Combat Air Program TAE, also known as Tempest.
The Tempest aims to field a flyable demonstrator within NIRS, featuring a virtual cockpit where physical buttons are replaced by AR projections.
Europe's other giant project is FCAS, a collaboration between France, Germany, and Spain to replace the Rafale and Eurofighter. FCAS places heavy emphasis on remote carriers, distinct drones that can swarm enemy defenses before the manned aircraft arrives.
Digital engineering is how these jets are born. They are designed, tested, and flown in digital twins before a single piece of metal is cut.
This drastically reduces development time and cost, allowing for rapid upgrades and modifications to counter emerging threats.
Modularity is key. 6th gen fighters will have open architecture, allowing hardware and software to be swapped out like apps on a smartphone.
Cyber warfare capabilities are integrated natively. The jet can hack into enemy networks, planting viruses or spoofing data mid-flight.
The cockpit of the future might have no windows. Some designs propose a windowless cockpit where the pilot sees through cameras and VR sensors.
This protects the pilot from laser blinding attacks, a growing threat in modern aerial warfare, while maintaining perfect visibility.
The jet monitors the pilot's physiology. If the pilot loses consciousness due to G-forces, the AI instantly takes control to stabilize the aircraft.
While stealth is priority, 6th gen jets retain extreme maneuverability through advanced thrust vectoring, useful if a dogfight becomes unavoidable.
Short field performance is essential. With bases vulnerable to missile attacks, these jets must operate from shorter, rougher runways.
Maintenance is revolutionized by 3D printing. Ground crews can print spare parts on demand, reducing the logistical tail required for deployment.
Range anxiety is solved by stealth tankers. 6th gen fighters will pair with low observable refueling drones to penetrate deep into enemy airspace.
The competition is fierce. China is actively developing its own sixth-generation concepts to rival Western supremacy in the Pacific.
Russia has teased the MiG-41, a hypersonic interceptor claimed to operate at the edge of space, though production timelines remain skeptical.
The race is on. It's not just about who builds the fastest plane, but who builds the smartest network. Let's look deeper at the connectivity.
Space integration is seamless. Sixth-gen fighters will communicate directly with low-orbit satellite constellations for real-time intelligence.
Passive sensing is critical. Instead of emitting radar waves that reveal its position, the jet listens to the enemy's emissions to triangulate them.
Advanced infrared search and track systems allow these jets to spot stealth enemies by their heat signatures, bypassing radar stealth. Thermal management extends to the nozzle. Serrated edges and ceramic composites mix cool air to reduce the infrared blooming effect.
Payload flexibility is vast. A single canister drop can deploy hundreds of micro-drones to confuse enemy air defenses. Cloud combat means no data is lost. If one jet is shot down, all the data it gathered has already been uploaded to the combat cloud.
The skin requires less maintenance. New composite materials are more durable than the fragile coatings used on the B-2 or early F-22s.
Automation in manufacturing drives down costs. While sixth-gen jets are expensive, automated assembly lines aim to prevent cost overruns.
However, unit cost is expected to be astronomical. Estimates for a single NGAD airframe range upwards of $300 million.
The power demands are unprecedented. The engine acts as a flying power station to feed the energy-hungry lasers and EW suites.
Operating altitude will increase. These jets will fly higher in the stratosphere, increasing kinetic energy for missiles and reducing drag.
Beyond lasers, high-power microwave weapons could be used to fry the electronics of incoming drone swarms instantly.
Pilot training is shifting to virtual reality. Pilots will log more hours in high-fidelity simulators than in the actual expensive airframe.
The human-machine interface is intuitive. The AI tracks where the pilot looks and highlights relevant targets or data automatically.
Weapons reach is critical. The AIM-260 JATM is being developed to outrange current adversaries, ensuring first look, first shot dominance. To carry these large missiles while staying stealthy, internal weapons bays must be significantly larger than those on the F-22 or F-35.
Enhanced landing capabilities may include thrust reversers or advanced braking systems to operate from bombed-out airfields.
Some concepts even suggest sixth-gen fighters could be air-launched from larger carrier aircraft to extend their effective combat range.
Software is the new battlefield. Millions of lines of code ensure the aircraft can adapt to new threats via over-the-air updates.
The UK's Tempest program focuses heavily on electricity generation, aiming to power directed energy weapons from day one.
The European FCAS faces political hurdles but aims for a fully integrated combat cloud that connects air, land, and sea assets. The US NGAD is designed to work in tandem with the B-21 Raider bomber, clearing the path for deep strike missions.
Cognitive electronic warfare uses AI to learn enemy radar patterns in real time and devise new jamming frequencies on the fly.
Despite high-altitude capabilities, terrain masking remains a viable tactic, supported by enhanced ground collision avoidance systems.
Voice control interfaces are being refined. A pilot can simply order
Wingman, engage target north.
Augmented reality glasses guide mechanics, overlaying repair schematics directly onto the engine parts, speeding up turnaround times.
Reliability is a major goal. The aim is to reduce cost per flight hour, which has plagued the maintenance-heavy fifth generation.
Only a handful of nations have the industrial base to build these machines. It is a high-stakes poker game of technological sovereignty.
Active protection systems will shoot down incoming missiles, similar to how tanks use trophy systems, adding a hard-kill defense layer.
The role of the pilot is changing. They are becoming mission managers, orchestrating a symphony of destruction from a silent cockpit.
If satellite links are jammed, the loyal Wingman can fly high to act as a communication relay node, restoring the network. Resilience against jamming is built in. AI filters out noise and spoofing attempts, ensuring the pilot sees the truth. Export potential is limited. The technology is so sensitive that nations may refuse to sell these jets even to close allies.
Timelines are aggressive.
The variable cycle engine produces a distinct blue hue in afterburners, a visual signature of the intense heat and efficiency.
Recovery of drones is the next challenge. Catching them mid-air or landing them autonomously on moving carriers is essential for reuse.
Secrecy shrouds the details. What we know is likely only the tip of the iceberg of what has already been developed in the black world. Air superiority is never guaranteed. It is earned through innovation, investment, and the relentless pursuit of the next horizon.